Hello, students. So let's try getting a little more exotic on our requirements for what we need in our ordered selection. So let's say we want to take an ordered selection of A, B, and C, but now we want an even number of each. So for some examples of this, what would be allowed? Well, we could have something like A, B, A, B. A would be fine. That would be an ordered selection of length 6. Also, we could have something like A, B, B, or A, B, C, A, B, C. The important thing to know is that these two are not equal because these are not just selections. As selections, they're the same, but they're ordered selections, and therefore none of these are equal. Of course, that one's a little more obvious. But we're requiring there to be an even number of A's, an even number of B's, and an even number of C's. For example, in these two, the number of C's is 0, so we get an even number of C's. So what could we use as our exponential generating function here? And let's think about this. Well, I don't want any x to the 1 because that's not going to be allowed. So if I'm coming up with the function for just the number of A's, I'm going to jump over to x squared. And then no x cubed, I'm going to jump over to x to the 4th. And so on. Okay, and keep in mind that as long as I'm going to include 4 A's, I'm going to need to divide by 4 factorial to compensate for the fact that I'm multiplying by n factorial at the end, but those A's are identical. Okay, but now what do I get entirely? Well, I'm going to get this cubed because I'm going to have one of these for the A's, one of these for the B's, and one of these for the C's, and all of them are going to be times each other. So let's think about maybe another way I can get an expression that gives me this thing in parentheses, so I don't have to write that out each time. Remember that e to the x is just going to be 1 plus x squared over 2 factorial, and I'll go out, I guess, to there, and so on. And I want to think about how could I get rid of all of the odd terms. If I could get rid of all of the odd terms, then I'd have that exact expression that I want. So what if I do this? Well, that would give me a negative at each of the odd terms. Now, if I were to just add these together, those negatives will all cancel out, which is excellent. That's what I want. But the other terms would all get doubled because I'd be counting this twice, this twice, this twice. So what could I do? Well, I could take 1/2 e to the x plus e to the minus x. And this is a very special function, which is called Cosh x. You might have seen this in calculus based on, where you took calculus from. Maybe, maybe not. It's a very important function, has lots of applications in engineering with things like the natural shape in which a cable hangs, but we're not going to do that at all because that's not what we're going to use Cosh for. We'll talk about it a little bit, but let's keep going here. While we're on a roll here, we did this very well. We were able to get a function that gets rid of all of the odds and keeps all of the even terms. Okay. We're probably going to need the one that keeps the odds and gets rid of the even terms, because what if we wanted an odd number of things? By the way, we can answer this question right now. I mean, it was already answered, but it's just Cosh cubed. So now I have a nice way of writing that. Okay. What if we just wanted the odds, though? What could I do? Well, let's see. If I wanted to get rid of the evens and keep the odds, what I might want to do is I might want to take the negative of this. Then I'd have a negative sign in front of each of the even numbered terms, and I'd have a positive sign in front of each of the odd numbered terms. However, what's going to happen there, I'm going to get all the odds twice, so what could I do? I divide by 2. So this is going to be called Sinh. So, sort of from calculus that if you have sine and cosine, you take the derivative 4 times, you get back to where you started. Well, with these hyperbolic sine and hyperbolic cosine, sinh and cosh, if you take the derivative 4 times, you also get back to where you started. But if you take the derivative twice, you get back to where you started as well. Let's think about that. What's the derivative of sinh going to be? Well, if I take the derivative of this, the only difference is going to be that negative is going to come down, it's going to become a positive, and I get cosh. If I take the derivative of cosh, what's going to happen? Negative comes down, and I get sinh. So, taking derivatives is something that we do with generating functions. In particular, does something nice to exponential generating functions. But even with normal generating functions, we sometimes want to do that. Let's say if we want to get the generating function for that gives coefficient n for x to the n. Well, you get there through derivatives. So that's something important just to keep in mind, that these are going to be the derivatives of each other. Okay. What are we doing right now? Well, we have these two functions. We have our answer to our first question here, which is how many ways we can have an even number of each. And maybe let's just plug this into Python really quick and make sure that this makes some sort of a sense. I'll pause so you don't have to watch me type. Okay, so what did I do? Well, just normally taking my symbol to be x. Cosh is a very well-known function, so it's definitely part of SIMPy. I'm going to take cosh cubed, and let's go out to the first 10 terms. If I needed more, I could go out as far as I liked. So now what I'm going to do is I'm going to multiply each of these by n factorial and see what I get. And I get this. And you know what? You might not like having this, you know, the cutoff gets factored into the first term here. So there is another way to do this. Instead of just asking for the coefficient of x to the n like that, you could say, hey, I want the coefficient of x to the n like that. And that takes care of that for us. So we're going to be sticking with sort of using this from here on. But okay, what do I get here? Well, you'll see. There's one way to not include any letters. There's 3 ways to do a 2-letter word. But there's no ways to do a 1 or 3-letter word. And why would that be? Well, that actually makes perfect sense because I have to use every letter twice. So I can't have a single letter, and I can't have 3 letters or 5 letters, right? It's always going to be a multiple of 2 if I have an even number of A, an even number of B, and an even number of C all together. So does this make any sense for the next term, the 21? Let's think about where that would come for the 4-letter words. Well, actually, it does make a lot of sense. We have 3 words that have, let's go really quickly. We have 3 words that are all the same, right? A, B, 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 and C, 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 C. But what about for the words that aren't all the same? Well, I have to choose 2 letters out of the 3 to put together. And then I have 4 spots. So I'm going to pick 4, choose 2 to place the first one. First letter, and put the others in the other spots. So what is this going to give me? Well, it's going to give me 3 times 6, which is 18. So since this gives me 4, I'm going to leave that in. Since this gives me 3, clearly there are 3 things listed here. 3 and 18 give me 21. 3 plus 18. And that's how I get to the 21 that we see here with the coefficients. Suppose we wanted to do another problem with odds. Well, let's do that in the next video.